SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 12. So, we will continue with our derivation for the formula for longitudinal strain, and we also will discuss about shear strain in this lecture. So, in the last class we had derived that the stretch square at a point x and for a line element with direction n. So, that was equal to n dot identity plus grad u plus grad u transpose plus grad u transpose into grad u into n plus this delta x term. Okay. So, that is the formula for stretch, and you remember. So, we started with the line element of magnitude delta x, but our goal is to get the strain at the point big X, and to do that we have to reduce the length of the line element and let it go to 0. So, finally, in this formula we have to apply the limit delta x going to 0. So, when we apply this limit delta x magnitude going to 0, then this term drops out, and what we have is simply n dot this whole thing okay. And you see, what was the reason to keep that big O term all along? It was just for us to ensure that we are not discarding any important term. See, it is always good to keep things, and finally, if it drops out, then it is very good, right. If we had discarded it right from the beginning, then we would never know whether that was important in the end, right. So, it is always a good practice to keep it from the beginning and drop it right in the end, not in the middle, all right. Okay, so, finally, we have this formula for longitudinal stretch square at a point big X and for a line element in the direction of n. And look at the terms here. This term, for example, you see it is grad u transpose grad u. So, this is quadratic in displacement gradient. So, you know, in this course we are only going to work with displacements such that the displacement gradients are very small. So, basically in this course we will only talk about displacements where del u I over del x j, its magnitude is much less than 1, it is very close to 0. So, del u 1 by del x 1, for example, is let us say 1%, 0.01, del u 1 by del x 2 is also of let us say 1%, 2%. So, it is very small than 1. So, think of what happens to the quadratic term here. You have grad u transpose into grad u. So, in the matrix form you have the matrix of grad u transpose into grad u. When you multiply, the components get multiplied. So, you will have things like del u 1 by del x 1 into del u 1 by del x 1 or del u 1 by del x 1 into del u 1 by del x 2. So, basically you have quadratic combinations of these displacement gradients. So, if the displacement gradient itself is very small 0.01 let us say, what happens to the quadratic combination? It is 0.01 square. So, it is even smaller, right. So, for this course we are going to drop this quadratic term. So, we will drop it. So, it is insignificant compared to grad u. See, we are saying that grad u is supposed to be very small in this course, but you also have, you see, identity here. The first term is identity, which is of the order of 1, and the grad u we said it is of the order of 0.01, 0.02. Then why do not we also drop the grad u from here? It is because if you drop it, you do not have anything. So, you have to keep the most significant term here and get rid of the less significant terms. So, the quadratic term here was lesser significant. So, therefore, we got rid of it. Okay. All right. So, finally, what we have is n dot identity plus grad u transpose into n, and you can make it even nicer. So, this is basically, you see the first term n dot. So, identity times the normal vector n, the direction n is simply n, and then n dot n gives you 1, because the direction is of unit magnitude, n is a unit vector. So, the first term gives you 1, and then the second term gives you grad u plus grad u transpose of n, and then the whole thing is further dotted with n, right. So, that is the lambda square. So, now we are ready to have the formula for the strain epsilon. So, epsilon longitudinal strain at a point x and for the direction n, for the direction of line element n. So, that is equal to, is not that lambda minus 1, the stretch minus 1, but lambda is then square root of what we derived here. So, it is square root of 1 plus this thing okay. And now this square root we can apply binomial expansion formula. See, it is 1 plus something which is very, very small, because you said that the displacement gradient are small 0.01 for example. So, you have 1 plus 0.01. So, this is very small. So, you could approximate this as 1 plus grad u plus grad u transpose into n dot with n, and then you get a half also. For the square root you get a half, and then you have the higher order term, but you then neglect it because grad u itself is smaller, minus 1, and now you see the 1 goes away, right. So, finally, we have a very small formula for the longitudinal strain, which is that epsilon is equal to half of grad u plus grad u transpose into n dot with n. Okay. So, that is the formula for longitudinal strain, the tensor formula. Can we, for example, try to think what will be the longitudinal strain when the line element is along E 1, the direction of line element is E 1. So, n is equal to E 1. So, then this tensor expression we have to write in the coordinate system of E 1, E 2, E 3, is not it. So, let us try to see what we get when we do that. So, we have half, and then grad u becomes a matrix in the coordinate system of E 1, E 2, E 3, which is going to be del u 1 by del x 1, del u 2 by del x 2, del u 3 by del x 3, and then you have terms here, you can guess what it would be. Plus grad u transpose. So, the off diagonals are going to flip here, but the diagonals remain the same. So, diagonal is still the same. But the off diagonals flip. Into n, and n is 1 0 0 now, because we say n equal to E 1. The whole thing has to be again dotted with n, which is 1 0 0. When you work this out, you simply get del u 1 by del x 1. Okay, so, that is a very simple formula. So, it is for epsilon at a point x, but for n equal to E 1. So, it is simply the diagonal of the displacement gradient matrix. Similarly, you can show that epsilon at a point x, but along E 2 is del u 2 by del x 2. You work out the whole matrix times vector, you get this formula, and likewise for epsilon at a point x, but for E 3 turns out to be del u 3 by del x 3. Okay. And for any general direction, you have to then put the value for n in this matrix formula, whatever is the n for the general direction. But for the directions along E 1, E 2, E 3, the expressions become quite simple. And can we see, is this formula does it match with what we learnt in the school? In school, for example, when we did that bar experiment, we had the bar and we apply some force. So, what is the displacement in the bar? So, displacement would be u equal to lambda minus 1 times x. So, when x is equal to 0 at the clamped end, displacement is 0, and as you go away from the clamped end, displacement increases, and it is maximum at the end where we are applying the force, and lambda here is the stretch. So, that is the formula for displacement. Can we see what is the strain? So, strain, we know that it is lambda minus 1, correct. If stretch is lambda, then strain is lambda minus 1, and what do we get from del u by del x? If we do del u del x here, we also get lambda minus 1. So, it tells me that the formula that we have derived is actually also making sense with what we learnt in school. It is just that our formula is more general. The formula in the school was quite simple for bars, but this is now for 3D body. You deform it in any way you want, and you want to measure longitudinal stretch, longitudinal strain at a point, then you simply apply this formula, the one in the red box. So, that is the formula for the longitudinal strain. All right. So, this was about longitudinal strain, and there is also something called shear strain. So, longitudinal strain, what does it do? It measures the change in length of line elements, whereas shear strain is another kind of strain which measures the change in angle between two line elements. Okay. So, let us try to work on shear strain now. It measures the change in angle between two perpendicular line elements. So, supposing this is the body and you have two line elements in the body. Initially it is perpendicular, and after deformation, suppose that the line elements become like this. So, that is the final angle between the two. So, what is the change in angle? So, if this is let us say beta, then the change in angle is 90 minus beta. Okay. So, if we say alpha equal to 90 minus beta, so that is the shear strain, the change in angle. And as you can guess, because it is measuring the change in angle, so it is also going to distort the body. So, this is the strain which is responsible for distorting the body. What will longitudinal strain do? So, longitudinal strain can change the size of the body. So, if you have a rectangular body, you apply some longitudinal strain, the size is changing, is not it? It still remains rectangular, but it does not undergo distortion. But if you apply some shear, the rectangle becomes a, so the angle between the edges of the rectangle is no more 90 degree, right? It becomes a parallelogram. So, that is undergoing distortion. Okay. So, shear strain is responsible for distortion, and longitudinal strain is responsible for change in length, for change in size. All right. So, we have to find out also the formula for the shear strain. Okay. So, let us try to work that out. So, I will just write here, it also distorts the body. Okay. So, again we have the picture for the reference configuration undergoing deformation, and suppose it becomes like this, and then at a point big X, think of two line elements, but perpendicular to each other. So, the first one, let us say it is delta big X, and the second one is let us say delta big Y. So, after deformation the big X goes to small x, right, and the two line elements they can also stretch. So, the length of the line elements can change of course, and the angle certainly can also change, but here we are interested in measuring the angle. So, the first one is delta small x and the second one is delta small y. Now, we had already derived that delta small x is equal to big F times delta big X, right, plus something of the order of delta big X square, right. And you can do the same thing for delta small y here, because we have another line element here. So, we can write it as big F times delta big Y plus something of the order of delta big X square. See, I want to keep these terms here, because we do not know whether it is going to become significant or not. Okay, so, what is the final angle of the two line elements? So, if we do the dot product of delta small x and delta small y, we get cos of the angle between the two, is not it? So, suppose that this angle here is beta. So, what is cos of beta? So, cos of beta is not that delta small x dot with delta small y divided by magnitude of delta small x times magnitude of delta small y, and then we plug in the formula for delta small x and delta small y here. So, we could say that the numerator for example becomes big F into delta big X dot with big F into delta big Y plus the higher order terms, is not it, and what is that going to be equal to? And of course, here this is delta big Y. Okay. So, I will simply write here plus higher order term, okay. And what is in the denominator? So, we have delta small x magnitude, which is nothing but the stretch of that line element times the original magnitude, and stretch is 1 plus strain. So, we have 1 plus epsilon for the delta big X line. So, suppose that this is originally in the direction of n, whereas this is in the direction of m. Okay, the directions are n and m, but perpendicular to each other. So, what we have here 1 plus epsilon at the point x, but in the direction of n, and then this is multiplied with the magnitude delta big X. Similarly, we also have 1 plus epsilon at the point x, but in the direction of m, multiplied with the magnitude delta big Y. All right. Now, we could also write this as, you see, why do not we bring this term here? and divide by delta big X here. Similarly, this term here and divide by delta big Y here. So, when you divide it, you again get the direction, right. So, we have f into n dotted with f into m divided by 1 plus epsilon, and let us call it n n, it is in the direction of n, times 1 plus epsilon m m. All right, and of course, you also have the higher order term in the numerator. Let us drop it for now, because it finally drops out. So, we are going to get rid of the higher order term in the numerator. So, and then the denominator, you see it is 1 plus epsilon, we have to bring it on the numerator. So, it becomes f n dot with f m times 1 plus epsilon n n inverse into 1 plus epsilon m m inverse, is not it? And epsilon n n, which is the longitudinal strain, it is very small compared to 1, right, because it depends on the displacement gradient, which for this course is much smaller than 1. So, we can again apply binomial theorem here, right, and we can write that 1 plus epsilon n n inverse is simply 1 minus epsilon n n, correct. So, this becomes f n dot f m into 1 minus epsilon n n into 1 minus epsilon m m. Okay. And of course, the next thing is to write your big F in terms of displacement gradients. Okay. So, this implies cos beta is then finally identity plus grad u into n dotted with identity plus grad u into m times 1 minus epsilon n n into 1 minus epsilon m m. Okay. And then we bring this on the other side, and we know that it has to become a transpose, and then you multiply them together just like earlier, and it becomes n dot identity plus grad u plus grad u transpose plus the quadratic term, you remember, which has to be dropped. So, we have to drop the quadratic term because it is insignificant compared to the grad u and grad u transpose. Okay. So, finally, what does this become? The first one you see n dot identity into m. So, it is n dot m, and because n and m are perpendicular, it simply becomes 0. So, we have n dot m, but this goes away because they are perpendicular, plus grad u plus grad u transpose times m, and then we further dot it with n. Okay. And we also have into 1 minus epsilon n n into 1 minus epsilon m m. Okay, now what can you say about the last two terms? See, grad u itself is of a smaller order. So, when you multiply the whole thing, the most significant term here is going to be grad u plus grad u transpose into m, and then you dot with n. That is the most significant term, and then you also have the remaining terms, but it is less significant because they are also multiplied with epsilon n n and epsilon m m, which are very small compared to 1. So, I will just write here plus insignificant terms. So, we can drop it, right. So, this is cos beta, the final angle, but we could also write it as sine of 90 minus beta, right. That is the relationship between cos and sine, but sine of 90 minus beta is same as sine of alpha, the change in angle. So, alpha is the change in angle, remember. So, that sine of alpha equal to grad u plus grad u transpose into m and dot with n. So, what do you think is the order of this sine alpha, given that grad u are really small, is not it? We said it is 0.01 or 0.02, 0.03. So, when you work this out, the right hand side is of the order of 0.01 or 0.02. So, sine of alpha, if it is very small, then sine alpha is same as alpha, is not it? So, we will write here, since right hand side is small, this implies sine alpha is close to alpha. So, that means alpha, which is the shear strain, is simply grad u plus grad u transpose times m dot with n. So, we have now the formula in terms of the displacement u. So, to measure shear strain between two line elements, one along m and the other along n, you simply use this formula. As you change the two line elements at a point, the alpha that you get also changes, right. So, I will just mark it in red, that is the formula for shear strain. Can we write down this matrix for grad u plus grad u transpose? So, the matrix form, let us say I want to do it for half of grad u plus grad u transpose. So, its matrix form in the E1, E2, E3 coordinate system. So, it is a big matrix, of course. The diagonals are simple, it is del u 1 by del x 1, then del u 2 by del x 2 and del u 3 by del x 3, whereas the off diagonals will now be half of del u 1 by del x 2 plus del u 2 by del x 1, and this will be same as this one here, and then we have half of del u 1 by del x 3 plus del u 3 by del x 1, and this is same as the one here, and finally, we have half of del u 2 by del x 3 plus del u 3 by del x 2. and you see it is symmetric because it is half of grad u plus grad u transpose. Okay. If you do the transpose of this, you get the same matrix. So, it is a symmetric matrix, it is symmetric. And the diagonal of this matrix gives you longitudinal strain, as we found out in the beginning, right, along E1, E2 and E3 directions. Let us see what is the significance of the off diagonal terms here. So, if we choose the two line elements, the let us say n is equal to E1 and m is equal to E2, and see what we get. Okay, so, if we choose the two line elements such that n is equal to E1 and m is equal to E2, then based on the formula that we have derived, alpha is equal to 2 times half of this matrix, right, grad u plus grad u transpose into E1 and dot with E2. So, can we see what we get? So, we come back to this matrix. If you multiply this with E1, you simply get the first column, and then you further multiply or dot with E2, you get the second component of the first column, and by symmetry that is this number, is not it. So, what we have here is 2 times half of del u 1 by del x 2 plus del u 2 by del x 1, which is simply del u 1 by del x 2 plus del u 2 by del x 1. So, that is alpha, we can say it is 1 2, is not it, because one of the directions is E1 and the other is E2. So, what we see finally is that in this matrix diagonals denote longitudinal strain and the off diagonals are actually the shear strains. Okay, so, let us try to also derive this formula through some pictures. So, suppose we have this big body and we are at a point x, and there are these two lines. So, this has size delta x 1 and this has got size delta x 2. Okay. So, after deformation the 3 points here will move, right. So, this point goes here, this point let us say comes here, and this point comes here, all right. So, basically this goes here, this goes here and this goes here. So, that is the line element after deformation. Okay. So, I will draw these horizontal and vertical lines. And notice what is the change in angle between these two line elements. So, it is getting basically due to this angle, the blue angle here and the green angle here. The two angles together gives me the alpha, the total change in angle, is not it? So, alpha has got two contributions, alpha blue plus alpha green. So, to get alpha blue, you simply look at this triangle here. What will be this distance over here? Why is this distance coming? Because the vertex and the tip point move differently in the E2 direction, is not it? That is why this difference came. So, if I can write it, this for example, that is u2 of big X plus delta x E1, is not it? You see this whole length, whereas this small length, that is u2 of simply big X, the vertex. So, this length is then the difference of the two, right. So, what can you say about alpha blue then? If it is really small, then alpha blue is simply the height divided by the base, is not it? So, alpha blue is then simply the height, which is u2 of big X plus delta x E1 minus u2 of big X divided by, so that is the height, the numerator, divided by the base, which is delta x1 itself, is not it? So, and you see what is this? That is the derivative del u2 by del x1, is not it? So, this is basically del u2 by del x1. So, alpha blue is basically del u2 by del x1. Whereas, the alpha green, through similar logic you can show that this is del u1 by del x2, and therefore, the total change in angle alpha is the sum of these two. So, now you can see what is the physical significance of this formula for alpha. So, it has two contributions, one from the blue and the other from the green. Okay. All right. So, I guess I am going to stop here, and then we again continue in the next class. We discuss more about strains. Okay. Thank you.